We are looking at a 5,000 share order.
Hey everyone, I'm Greg Baugues and welcome back to Google Cloud Live. Today I am joined by Jeff Nelson from Google Cloud and Will Hill from NVIDIA. Gentlemen, welcome to the show.
Hey there.
Well, what's up? Jeff, could you introduce yourself?
Sure. I'm Jeff. I'm a developer advocate here at Google Cloud, and I focus mostly on data analytics, data science, and those types of workloads.
Amazing. And Will?
Hey, Greg. Yeah, I'm Will Hill or William Hill. I'm a developer advocate at NVIDIA, primarily focused on, Python, open source, data, quant, those sorts of libraries to accelerate on the GPU.
Amazing. And Jeff, what are we talking about today?
Sure. So we're talking about how to use GPUs to accelerate our data workloads. When we think of GPUs, or at least when I think of GPUs, today, I think a lot about large language models, training these big models. In the past, I used to think about gaming. GPUs, to me, feel like a little bit specialized hardware that might be reserved for certain types of heavy graphics or heavy AI researchers. But something that's really neat is that we can apply them to our day-to-day data workflows. They can take our traditional data frame operations and make them much faster. So yeah, in today's session, we're going to talk about how to parallelize workloads like Pandas workloads or scikit-learn workloads with GPUs and apply it to our day-to-day work.
Amazing. So if you're a developer, if you're a data scientist, you're doing work with data, especially large data sets in Python, this is going to be a great conversation for you. And Jeff's going to kick us off with a demo.
Awesome. So I guess, Greg, give me a city. Just throw anything out there.
Yeah, let's go with I'm in New York, so we'll start off with New York, and I would also love to hear from the chat for folks who are joining us where you all are calling in from.
All right. So this is a climate analytics dashboard. We show a bunch of cool climate data here, and this is running on a GPU, and it's using CUDA and QML. These are NVIDIA libraries that carry out our data frame operations. And as we continue to add more and more cities to this, we can continue to get those insights back super, super fast. I'm in Los Angeles, so I'll type Los Angeles, and we get this back. We get some climate data back super fast. Greg, do you see any other cities in the chat?
We have here, can we do Ho Chi Minh, Vietnam?
Trying to spell correctly. All right, Ho Chi Minh, there we go.
Amazing, that's so fast. And can we do Bengaluru, India?
Nice.
Try to spell things right here. All right, cool. And the closest weather station that we have was 0.8 miles away from where we said. And we get those insights back right away.
All right, so can you talk us through a little bit, what is the data that's powering this? I see a really big number up on the top there.
Yeah, so the data that we're talking about here is it's like 340 million records of weather data. This is data taken from the Global Climatology Network. It's pretty much the source of truth for a lot of weather data. It's actual recordings from stations on the ground, and in some cases, depending on the station, going back to the 1700s. So this is really cool data. We also have some station metadata, coordinates, things like that. And that's how when we type in a city here, like London or anywhere really, we're going to get back these insights. Now, what's also happening is we're chewing through 340 million records to get these insights back. In this case, we're looking at TIP London, and we have 39,000 or almost 40,000 records matched. So these are all of London's records in this data set. And it took about 88 milliseconds to return this.
Wow. All right. And this is an app that you built. And this app is hosted where right now?
So this app is hosted on Cloud Run. Cloud Run has a GPU attached to it, and it's running these data frame operations on the GPU itself.
And then where is all the 340 million records? Where is that stored right now?
Those are stored in GPU memory on the Cloud Run instance.
Incredible. And so it's able to query against 340 million records. It's able to find here about the 40,000 records for London that were relevant, and it's able to do all that in about 90 milliseconds.
Yeah, 80 to 90 milliseconds. That's right. Okay. Now, something I do want to show is where a lot of us are used to using pandas for our data workloads. So I'm going to move over to a different tab, and this is a pandas. This is a different Cloud Run instance, and it's going to use pandas for everything. So it's not GPU accelerated. So if we type something in here, let's see. Do we have any other cities in chat, Greg?
We do. We had someone from the Netherlands. I don't know that I have a city name. I don't know if it's going to work without a city name.
Well, it did. It's working.
Okay, great.
And it found a station in the Netherlands, and that looks right on the map. But that took about 9 seconds to compute. So when we think about the disparity there, it's pretty big.
Jeff, would you able to do a side-by-side? Is that possible?
Yeah, I actually do have the side-by-side actually ready to go. If we have one more city, I'll throw that in. I'll throw the GPU version and the CPU version next to each other. Any cities?
Can put NOLA, just NOLA, New Orleans, Louisiana.
All right, we'll try that out.
Humid.
There we go. We get the result immediately on the GPU side. It took 95 milliseconds against 340 million records again. And we're still waiting on the CPU side. All right, there we go. We get the results back. It took about 9 seconds, or about 10 times as long.
So what you're saying is it took way longer with less data. And if I'm looking at it, your results aren't the same there.
Yeah, so on the CPU side, we're looking at 113 million records here. On the GPU side, we're looking at 340 million records. So the GPU has about 3 times as much data, and it's almost 100 times faster. So the insights are a little bit different because we're only able to go back so far on the CPU. On the GPU, we're able to ingest all of the data.
And so for the CPU, you had to sample, and you were only actually able to work against less than half of the records. So you're not only getting like a couple orders of magnitude of improvement with performance, but you're also getting much greater accuracy with the GPU.
Yeah, we're querying against quite a bit more data with the GPU. That's right. And it's incredible how fast this updates. I mean, we could continue to just put in other cities, and we're going to continue to get these results back just blazing fast. We're not querying anything that's pre-aggregated. There's no tricks behind the scenes. When we think about this GPU side of the story, we're going to show exactly how this works. But every data frame operation here is running on an NVIDIA L4 GPU that we see here using CUDA, which is a library that we're going to talk about in just a second.
I would love to learn more about that. That feels like a good time to hand it off to Will. Will, could you tell us about what is making all this possible here?
Sure. So, at the hardware level, we all know GPUs, right? Whether you have a 5090 in your gaming rig or you're familiar with these data center GPUs like Jeff was just showing here. But there's a couple layers above that physical GPU, right? There's the CUDA layer, which is kind of the groundbreaking thing. One of the things that NVIDIA came up with, which allows you to control the GPU, right? It's an API. You can program the GPU to do what you want. Now, for a mere mortal like myself, I don't do C++ programming. I'm doing data stuff with Python. So for those like myself, we have a whole layer, a third layer on top of that. So you got the physical GPU, the CUDA layer, and then you have these CUDA X open source Python data libraries. So like CUDF, QML, like I'm going to talk about, those are Python libraries, open source, right? If you know pandas, then you already know how to use it. If you know scikit-learn, you know how to use it. And that's what we're talking about today.
I have a ton of follow-up questions here. I want to start, I thought it was interesting. You said, we're all familiar with GPUs. Obviously it's something we've been hearing a ton about in the news. Maybe there are folks here who, could you just start at the foundation? What is the difference between a GPU and a CPU, and why does that matter in this context?
Sure. Yeah. So, the CPU was designed for the computer, the operating system. It's designed round robin. It operates sequentially. A GPU was designed to operate in parallel on large matrices or frames of data. And so that's why it pairs so nicely with things like pandas data frames or SQL databases. And so the GPU is essentially a massive parallelization, if I said that right, parallelization, machine, right? It's basically a supercomputer for doing tons and tons of floating point operations in parallel, whereas the CPU is meant to be sequential and to handle lots of, operating system type operations. It has a much larger instruction set than you would need to do floating point operations. And
then what is CUDA?
All right. So CUDA, like I said, you've got that GPU, but I want it to do more than play games or I want to program. I want to control it to do data operations, which we're talking about right here. So CUDA, again, is a C++ library on top of that GPU. And then, like I said, there's also CUDA X, which is a higher abstraction. CUDA X allows you to do Python programming, which, calls C++ libraries written in CUDA, and then runs those operations, your pandas or scikit-learn, on the GPU massively parallel.
Okay. And then, forgive me, I don't know exactly how to pronounce this. CUDF?
Yeah, it's interesting. I had the same problem. I kept seeing these words, but before, years and years ago, I kept, what the heck is this little c, little u, and then ML and DF or graph, right? And once I got it, it kind of stuck, right? Once I got it. So we have, like I said, we have the NVIDIA GPU, CUDA, and then CUDA X. So that CU, the little CU, stands for CUDA X. And the ML is machine learning, or little cu for CUDA X, and then DF for data frames. And so that QML, as I say, QML, that accelerates our open source machine learning library, scikit-learn. And QDF accelerates pandas, polars, SQL, Apache Spark. And we have a bunch of these higher abstraction Python open source libraries. Like another one is QGraph, which is CUDA X for graph analysis, which accelerates Network X. Same thing. You don't have to change any code.
So these are libraries. They're open source libraries that were developed by NVIDIA to serve as a bridge between the Python data analysis tools that folks already know and use and the NVIDIA GPU hardware.
That's right. And there's actually a whole bunch of these libraries. Like recently at our GTC event, Jensen was on stage and he showed just the whole breadth of so many industries these CUDA X libraries cover, right? And we're just like today, we're talking about primarily the data analysis, data, machine learning, data science libraries here. And it's just, I want to go fast, but I don't want to write C++, right? It's for people like me.
Yeah. And Jeff, how does Google Cloud come into play here?
So Google Cloud allows you to access NVIDIA GPUs, and a lot of our services that allow this access already have these popular libraries installed on them. So when I booted up this Cloud Run instance to use CUDF to show these super fast climate insights, I didn't have to go manually install CUDF. Additionally, when we look at Colab Enterprise, which is the kind of REPL environment where we can be a little bit more interactive, the Colab Enterprise runtime with a GPU attached already has these libraries installed, so we can just get started right away. So on the Google Cloud side, we allow you to access GPUs, and many of our services already have some of these libraries pre-installed.
And is it like a lot of work for a developer to start using these, or how do they go about starting to do that?
No, it's not a lot of work, and we'll show you exactly how this works. I think the coolest thing is that once you attach a GPU to your notebook in Colab Enterprise, which we'll show in a second, the only thing you need to do is add one line of code. It's this load extension. We'll call it this like magic statement. So if you know how to run pandas workloads in Python or scikit-learn in Python, all you need to do is add this one line, and all of a sudden you're running on GPUs using cuDF or QML.
Very cool. And you have a demo for us to show this?
Yeah, absolutely.
Would love to see it in action.
Awesome. So here we are in Colab Enterprise. This is in Vertex AI. So if we look at Vertex AI, scroll down to Colab Enterprise, that's where we are. Now, I'll get to the demo in just a second, but before we do, I want to show you how to even set up a runtime that is kind of the machine behind everything that we run. And I'll begin with a runtime template. Now, a runtime template allows you to create additional runtimes in that templatized format. I'll create a new template, just call it something like demo. You can choose your region, continue. And this is where the meat of this runtime template sits, is the machine type. So not every machine type has a GPU attached to it. When I scroll down and I look at something like G2, the G2 class has NVIDIA L4 accelerators or GPUs that can be attached. The A2 class has A100s. And I think there's probably like the A3 has H100s. So we give a variety of different GPUs that can be attached to different types of machines in the Colab Enterprise environment. Of course, when we look at other services too, like Cloud Run, we have a very similar story. So I can set this and say, hey, this is going to be my template. But I also really want to emphasize this idle shutdown parameter. So I can set this to like 30 minutes or 10 minutes or something like that, because I do not want my GPU to keep running if I'm not doing anything on it. Because one of the worst feelings in the world that I've had as a developer is getting a bill about a week later because I left my GPU running and I didn't do anything about it. And I wasn't running anything. There was nothing productive happening. It just kept going. So I definitely encourage you to set this idle shutdown parameter. You can set it between 10 minutes and a day. I usually set it as like 30 minutes or so, but it's up to you. We can choose the Python environment and things like that, but I'll click create. And then we have this runtime template from which we can create a runtime. And it has all of the details that we just talked about a second ago. Now, this does take a couple of minutes to boot up. So I'm not going to, I could create it, but I do have a runtime that is already running, and we will use that. So here it is. We can see it is a G2 standard 12 with an NVIDIA L4 GPU attached to it. The idle shutdown time I set to 30 minutes. I like that as somewhere in the middle ground between like 10 minutes and 1 day.
Cannot overstate the importance of that idle shutdown for the folks who are watching the stream and playing with this for the first time.
Now, Greg, if it's too short, I actually, mine just ran out and I had to restart mine because I set it too short. Just beware, you want to make it too short because, you go get your coffee, come back, you want that thing still running. Just FYI.
Good. All right. So 10 to 30 minutes is a good for folks who are just getting started here.
Yeah, I'd say 30 minutes is probably good,
Awesome.
but up to you too. So, all right, so I have this runtime, and this again is the compute engine on which we will run everything, but we need to look at the code. So I have a notebook in here. Specifically, we'll be looking at the climate data again, and kind of showing you how it works behind the scenes. What I want to show is just like kicking things off. It looks like this is already attached, but if a runtime was not attached, I can kind of go up to this top corner click change runtime or attach runtime, and I'll connect to an existing runtime, which is the one I have running. You can see it's the same stuff we just looked at. So this is good. It is connected. And I'm going to just kick this off because loading the data in takes a little bit of time. It takes maybe 30 seconds or so. We're loading in the 113 million records, again, because we are going to do operations on the CPU. And again, this is the global climatology network data, that kind of source of truth for climate data that goes back in some cases to the 1700s and has several thousand weather stations. Now, when we look at this resources pane here on the right side, I can click this this little box up here and it makes it come and go. But what we see is the system RAM has now gone up from 0 to 10 gigabytes. And the reason for that is we just loaded in about 10 gigabytes of data onto the machine. We can see this down here. We loaded 113 million weather records and about 8,000 weather stations. So this over here, this resources pane, is really a great way to keep a handle on how much memory are you using? Because what we often see, especially with Pandas workloads, is this spikes, it hits the limit, your runtime crashes, and you need to start over. So keep an eye on that. This machine has a healthy amount of RAM for what we're doing today, so I'm not too worried about that. We could take a quick look at the data frame. Again, we called the data frame with the 113 million records, DF. Just look at the top 5 records, and we could do things like display a histogram of the maximum temperature for all of our weather stations. So just to give a little bit of descriptive statistics, it runs pretty quickly. For everybody else outside of the US, apologies, this is in Fahrenheit.
Convert it for us, Jeff. Convert it for us.
I know. It was actually in Celsius, and I said, oh yeah, I'll convert it to Fahrenheit. And now I think this is not the best. All right, so
wait, I just want to be clear that that's a summary. That's a distribution that was just done across over 100 million records.
That's correct.
That's kind of wild.
It's great. And this was using the CPU, actually.
That's using the CPU.
We barely saw it. This took, you can see it's very small here, but you can see this took 3 seconds to complete.
Okay.
If we threw it on a GPU, we'd probably get a little bit quicker, but with 3 seconds, I'm not too worried about things.
Okay.
Now, when we thought about this dashboard, just going back to this dashboard, how do we populate things? When I type something in like, I think we use Fairbanks, Alaska as an example, we do a lookup against what is the closest weather station to the place I input. And that happens to be the Fairbanks International Airport. So when I do the same thing here for Fairbanks, this is the latitude, longitude, I'm going to return the closest station, which is again, exactly what we saw on the dashboard or the web app, Fairbanks International Airport. So we're going to use this in the example. Now, again, when we looked at this dashboard, we saw things like the hottest recorded date, the max daily rainfall, the coldest recorded temperature. And we will calculate this with data frames or these data frame operations right here in the Colab notebook. So if I run this cell, we will get our insights back. It takes a couple of seconds to run, but this is exactly the code that's running on the Cloud Run instance that powers that web app. So we get these results back. It differs a little bit from what we just ran because we're running on the 113 million records, not the 340 million records, but we do get those results back to us. Again, these are data frame operations that are right now running on Pandas on our CPU. Now, when we talked about that kind of magic command, this is where kind of the magic happens, and this is what I'm really excited about. When we run import pandas as PD, as many of us do, we see the module is located on this runtime, and we see where you kind of just see where it's located. If we run this one command, and this is what I want to emphasize, load the extension, CUDF.pandas, we're going to get a result, and it's going to say, okay, module pandas, but we have this accelerator, and we're going to use CUDF to make it really fast. And if we need to, things will fall back to the CPU and use pandas. So it's really that simple as loading this extension, CUDA-pandas, and then we're good to go. So we'll show how this works, but we'll kind of show a side-by-side, but I do need to restart the runtime just to make sure we're keeping apples to apples here. When I restart the runtime, of course, our RAM resets back to 0. We don't have any data back in memory. So what I want to do here is compare the latency between CPUs and GPUs for this specific weather example. What we have here is a function that takes an input and has the latitude, longitude hard-coded right now, but it's looking at the same logic. It uses the same logic that we just showed a second ago. So we're filtering, or we're finding we're doing the geolocation. We're getting these min, max, precipitation, things like that. And this is a function that will run both on the CPU and the GPU. So we'll define that function, and we'll run this on the CPU just to begin with. And this takes a little bit of time to run through. If we again look over here, we'll see that the RAM starts to go up on the CPU as expected as we're loading in this data. And after the data is loaded, it will run the data frame operations to get the min-max temperature and a couple of other things. So we see this returns, took 17 seconds to load the data and about 8 seconds to do the computations. Kind of similar to what we saw over on the web app. Now we have the exact same code down here, but we're running it on the GPU. Make it a little bit bigger. But the difference here is that we have the load extension, CUDA-pandas, at the beginning of our cell. So when we run this, we'll see it complete quite a bit quicker. And we'll also see that the GPU RAM should start to increase as well, because we now have data on the GPU, not just the CPU. So we see this took 4.5 seconds to load the data and about 1/3 of a second to do the computations. Now, if I run this again, something that's really interesting, I think, is that it should drop by quite a bit, right? So now we see it took about 1/10 of a second, which is in line with what we saw on the web app. Now, what's happening here is, I think it's a good example of how the GPU hardware works. That initial delay is the hardware kind of waking up, allocating its memory pool. And once it's initialized, it's going to be super, super fast, as we saw here. I can visualize this speed up, or actually before I do, if I was to run this CPU operation again, I might see a slight decrease in this, about 8 seconds, but nothing to the effect of what we saw on the GPU. It's not going to be 1/3 of the time or 1/5 of the time. Now, just looking at the visualization of the speed up, we can see, make this a little smaller, it's quite a bit faster when we use the GPU. And all we needed to do, again, was load that extension, that magic function, and here we go. One other thing I do want to show is sometimes you're running operations on a GPU and it's slow. And you want to figure out what is going on. And this is where we have another magic function called CUDA-pandas.line profile. And this goes line by line and figures out where things might be spilling over to the CPU from the GPU. For example, maybe CUDA-pandas doesn't have some kind of thing that's implemented yet. It might spill over to the CPU and use traditional pandas to get that result. I guess in this example, so we have these different lines. We see everything is run on the GPU. We don't have anything on the CPU time. And that's okay. That's what we'd want to happen. But if operations were spilling over to the CPU, we would see this CPU time column filled as well.
A couple questions. First off, if someone's watching this right now, they're doing data stuff with Python. what is a signal to them that they might want to start using GPUs instead of CPUs?
Yeah, that's a good question, Greg. If you run your code and it doesn't come back immediately, for me, that means I have things to do. If I run my code and I find myself doom scrolling instead of coding, that's a good sign. Here we go. Let's use the GPU. But seriously though, like Jeff was just saying, if you fill up that CPU memory or your system memory, and you're going to spill over to disk, or you're going to crash, right? That's a clear sign. All right, I'm going to save myself a lot of time using that GPU because it has memory and it can, like Jeff was saying, it can actually spill over to the system. So you can kind of stitch both memories together and fit your data frame in there. That's called a unified virtual memory. It's really cool because if you were noticing when Jeff ran that code and it filled up the GPU, it filled up the CPU too. And the reason it does that is because if an operation is not parallelized on the GPU, it'll seamlessly just run on the CPU, okay? And put that result, those two data frames need to be in sync. So again, to answer your question, I'm going to use my GPU for me always, right? But if you have some rules of thumb are, if you have 10 million rows of data, that's a good sign you should use a GPU. If you're doing some heavy operations, you're merging and grouping and you're kind of consolidating rows of data and then also doing calculations, right? If you're summarizing rows and you're spitting out calculations, averages, variances, that heavy number crunching is what this GPU was built for. Or rather, that's what CUDA was built for, and CUML are built for too. GPUs built for a lot of things, but CUDA and CUML are built for to do that number crunching with your pandas, with your scikit-learn. So, yeah, like you said, I always use it. But for you, if you start running your code and it's slow, might as well click the GPU button. Everything's already installed in Colab Enterprise, right? You don't have to install any extra libraries or anything.
So if you're using pandas already and you're getting to millions of records, tens of millions of records, you're tired of waiting for those operations to complete, probably a good time to try to spin up a GPU and see if you can start using those. And those will complete a lot faster. Is it also going to get a lot more expensive?
Yeah,
I don't. Go ahead, Jeff.
GPUs are definitely more expensive per hour than an equivalent CPU-based machine. But if we think about the math, like with this example, I think we had like an 80x speed up or 100x speed up. If your workloads are running that much faster, even like 10 times faster, your bill, your total spend could be going down because you're only paying for 10 seconds of compute instead of 10 minutes of compute, or 100 seconds of compute, or whatever it may be on the equivalent CPU side.
Oh.
That said, I will also continue to emphasize that you should be judicious about shutting down your GPU machines when you're not using them. They're great to accelerate things, but again, one of the worst feelings as a data practitioner is leaving a GPU running and not using it. So I encourage you to shut it down once you've used it. But yeah, something to think about. And it also depends on your use case. So I'd encourage people to check things out with their own data, because some data is different than others.
Yeah, that's a good point. The way I think of it is, if I'm using a VM or any cloud resource, I don't want to spin up resources I'm not using at all, right? And I generally have a goal. I'm trying to win a Kaggle contest. I'm joking. I'm not doing that. But I'm trying to deliver some insights from my data, or I'm trying to converge on a model for a solution of some sort, right? That's the goal. And so, like Jeff was saying, if you spin up that GPU and you're doing hyperparameter optimization, you might converge on you likely will converge on your goal, your end solution, or whatever it is you're trying to do so much faster. Number one, your sanity, your mental health is there because you're not watching code spin. And number two, you get to shut that machine off, 10 times sooner.
That makes sense. Yeah. So it's going to be trade-off. It depends on what you're working on, how quickly you want the results, how much you want to iterate, and then of course on budget. And then there are controls in place there for you to control how long you're renting that GPU instance so that you can control your costs.
Yeah.
Yep.
All right. So
I'll also say like the last thing here is like people assume again that when we need to run things on GPUs, as Will was talking about earlier, we might need to write a bunch of C++ or some sort of low level language to do this. But in reality, you don't need to rewrite your entire code base. You don't need to learn new frameworks just to get the benefit of GPUs. As we showed just a second ago, you literally load an extension and your existing pandas or scikit-learn workloads run quite a bit faster. So you don't need to worry about that type of migration. And on the machine learning side, we have something very similar. And I think that's what I want to pass over to Will. Will will show us exactly how to do this with machine learning workloads.
Amazing. Will, take it away.
All right. So just like Jeff was showing here, I've got a notebook here, but instead of being I'm obviously using pandas. That's what I use. But I'm also going to do scikit-learn, right? And like to answer your question, Greg, if I were to run this, this notebook, and this is kind of a basic example of machine learning, data science pipeline that I'll show you here. I can turn this off, I think 25 times sooner. So let me just run through.
Will, I'm sorry. Could you make this just a little bit bigger?
Sure thing. Sure thing.
I feel like my eyes are going.
Hey, Will, could you get rid of the fair on the right side? Just exit out.
This one right here. Sure
Yeah, it makes it a little bit bigger. And if you need the table of contents, keep them. But otherwise,
I don't.
Cool.
Awesome. Thank you.
All right. So, just to check here, I always like to do, you can also do this. I've got my system RAM, my GPU RAM. As you can see, I'm loaded up here. And you can actually see I'm on an L4 and I have actually more memory than I have system memory. So, I can load more data. And then, like I said before, if we spill, we can combine these two memory systems. All right. I've got 4 CPUs and I've got plenty of memory. So I'm going to do a little data science here, a little analysis. And let's say I'm a taxi driver in New York City, and I also do a little coding on the side. And I want to know where are the best fares? Where's the best tips? That sort of thing. So I've downloaded the data, and this is actual, yellow trip data from New York City hosts this. This is open data. And then we're going to start doing a little bit of data science pipeline here. And again, this is more to show the ease of using the GPU more than, the accuracy. So if you've done this sort of thing before, you'll recognize a lot of this, right? I'm going to grab my data. I'm going to do a little feature engineering, a little more feature engineering here. And then I'm going to split my data. Let's see here, down here using scikit-learn. And then I'm going to do a couple of models. First one is random forest, and I'm going to do 50 trees or 50 estimators, and then also XGBoost, which is also natively GPU accelerated. Only thing you have to do is set device to CUDA, and that will make it run on the GPU. Okay. Just like pandas, to make this run on the CPU, on the GPU, I have that magic command, which I'll show in a second. But I'm not going to run this on the CPU because you'll see why here in a second. That random forest took over 5 minutes. The XGBoost took 2 minutes. And I also have this kernel density estimate because as a taxi driver, I need something visual. Where do I go set up? Where do I go pick up the fares? And I'll show that in a second. All right. So all of this ran on the CPU. And if I can do some math here, 5, almost 6 minutes plus another 2 minutes. It's a long time. Let me just say that it's a long coffee break. Okay. So to do the same thing, I'm going to run this magic command that Jeff already showed. And then I'm also going to do this QML, CUDA-X for machine learning. And we have Excel. And just to explain what this is again, this is going to take scikit-learn code. You don't have to change anything. You just run this before the import. As long as you run this before your import, anything that is parallelized on the GPU in scikit-learn is going to run on the GPU. All right. And this one I can actually run. I can run this live, right? Let's see here, because it took 8, 10, and less than a second. All right. So again, this is going to grab taxi data. It's going to do a little bit of feature engineering, and then I'm going to build a random forest using just the standard scikit-learn fit. That scikit-learn API that we all are all familiar with. Same thing with XGBoost. And that thing is done in, this time it was 3 seconds, 2.5, and less than a second. All right. I saved both of those times because what are we doing as data scientists if we don't have plots, right? So I made this super handy plot right here. Yes, I vibe coded it. It's a bunch of HTML in here, but this is the comparison of the CPU versus the GPU. Obviously, longer is worse, right? So that CPU took, let's see, 347 seconds, and the GPU was 8 seconds, right? XGBoost 2 minutes, and this took 11 seconds. And then that kernel density estimate was 44 seconds on the CPU, less than a second. So over here, I have how much faster it was. So 44 times faster, 11 times faster, and almost 100 times faster to do that kernel density estimate that I'm going to use for my taxi driver map that I'll show here in a second. All right. Same thing. When my code is slow, right? I want to know, why is my code slow, right? Is it me? Did I do something wrong? I take it personally when my code is slow. I want to know, what did I do wrong here? So we have the same kind of analogy with CUDA pandas. We have this profiler here. I can just run it. And it will, we have two profilers. We have like this kind of overhead generalized one, which shows me that all of these functions did in fact run on the GPU, and it shows me the time. Now, if it didn't, if there's something wrong, or I didn't, it'll show me which code runs on the CPU, and then I can adjust. For a little more granularity, I have this line profiler, and this is going to show me much more. And like I said, this is really, what I really like about this is, generally when you profile your code, it's kind of a headache, right? In your VS Code or whatever you're running, there's, a multi-step process. Here, I just put this magic command, right? That's pretty powerful. So here is that detailed layout of the profiler. If something is super fast, obviously you don't care about it. But you can see here, all of this was on the CPU. And then we can see here, my random forest fit and inference were on the GPU. All right. So now that I've got my model, I'm a taxi driver. Where do I get the biggest fares? Where do I get the biggest tips? So I decided to make a nice little heat map using that kernel density estimate. And again, I'm not going to run it on the CPU because this time around I did even more data and it took 17 minutes. Okay. We don't have 17 minutes to sit there and draw a map, right? I'm a New York taxi driver. I barely have a New York minute. So here's all that kernel density estimate code where I'm looking at fares. I'm doing, very, very dense analysis here, but I need to know. And so this right here is that kernel density estimate, that heat map. And you can see on the right here, I have the total fares. I have the tip, the tolls. Apparently JFK, right? That's pretty far out there. So it makes sense. I'm going to take long fares. People are landing at the airport and going wherever. Same thing for LaGuardia. And then you can see where are the tips, right? We've got Harlem. We've got, looks like Midtown Manhattan. And I don't know New York that well, but people in this area seem to tip well. So that's kind of the scikit-learn on a GPU, right? In Colab Enterprise, saving you, in this case, I don't know, 27 minutes versus a few minutes, right? I think that's pretty powerful stuff.
The number one question that we're getting in the chat here is the notebook publicly available?
Jeff, do you want to take that one? Not this exact notebook, but I'll let Jeff take this one.
Yeah, sure. So probably not this exact notebook. We could make this available,
Yeah,
but
I'll put it
we
out there.
do have two full learning paths. One that looks more at CUDF and one that looks more at QML, and both of them actually use the taxi data. So yes, those are publicly available. If they're not already in the show notes, or we don't put, they will be on the show notes after the fact if they're not already there. But yes, there are two learning paths that go through this. They have very detailed examples, samples, Colab Enterprise notebooks. I mean, you can run them anywhere, actually. They're just Jupyter notebooks. But yeah, this is all publicly available.
And if you're watching this on YouTube later, it should be down in the description. All right. Moving to some questions here, and I'm going to start with one of my own. I think we have a lot of folks who are early in career. We have a lot of students, like grad students watching. If they haven't played with this stuff before, where's a good place to start? And where is a good place to, say, get their hands on 100 million rows of data to play with this? Like, how do you dig in and just start playing here?
Just going back to that last answer, I'd say check out these learning paths that have the sample notebooks and they'll also pull in the data for you. So You'll get that data, you'll be able to run it. You could run this on Google Cloud, on Colab Enterprise, or you could run this on the standard Colab consumer, which is totally free. And you can also attach a GPU for free there as well. So I'd recommend starting somewhere in that realm.
Awesome. Will, you have any thoughts, any general thoughts on just how folks get started here?
Yeah, for me, I got, like a lot of people, Kaggle, and Kaggle, is run by Google. So they also have really nice data sets and kind of sample problems. They also have learning courses. If you graduate from the learning paths that Jeff and I maybe go, NVIDIA also has DLI Institute. So if you want that kind of structured, sequential learning, those are good ways. But if you want to do your own exploration, right, go grab a data set and just model what you think of, right? Whatever interests you, go find that public data set and try to model something and just play with it. Using open source tools. That would be my recommendation.
It's sort of astonishing how many.
I just like to piggyback off that, Will. I always like, when we think about these data examples and how do we want to get started and what's interesting, like find something that you're really passionate about and use that data. Yeah. We just finished March Madness. I love basketball. I like to use basketball data. It's fun for me. So I love using that type of data. If you like a different type of climate data, for example, use that. But finding data that you actually like for whatever reason, maybe it's a hobby, maybe it's some sort of interest, start with that.
Yeah. True.
It's amazing how much open data is available out in the world for just about any interest that you're into. And then I think a lot of it just, my guess, it starts with curiosity too. Like what's your topic of interest? Can you find data around that? And then what are the questions you want to know about that? And then you start figuring out how to answer those. I had a question here from Ramesh. Is it possible to load multiple CUDAs in multiple GPU environments?
So there's Dask. There's Dask, which is a multi-node. If you want to start doing multi-node, open source Dask is probably the way to go. Or another GPU acceleration multi-node is Apache Spark, right? That CUDF that we're talking about here accelerates both of those.
You said multi-node. Could you talk about multi-node a little bit?
Yeah. So we were talking earlier about when you use CUDA, when you use these CUDA X libraries, like a good example is that CUDA F, right? And as you start reading in that Parquet file, as we showed, as Jeff showed in the Colab Enterprise, you can see it filling up, spilling over to system RAM. And then at that point, if your data set is too big to fit on one node, which is what Pandas is built for, you can do one of two things. You can sample your data down till it fits, or go into a multi-node setup with a library that was built for multi-node, like Apache Spark or Dask.
So that's when you're getting to really, really large data sets.
Yes.
Had another question here from Ira. It said, are there any limitations in QML on Colab we should watch for, like the dataset size, GPU memory, supported algorithms? So this feels sort of related to what you were just talking about here. Like what sort of limitations should they be looking out for? When are they going to bump up against the edges of what these things are capable of?
Yeah, it's going to run just same as you would run it anywhere. What's nice about the Colab Enterprise is you can customize, like Jeff showed in the beginning. If you want a larger GPU, if you want a larger VM, you can do that. But that QML is going to run the same no matter which GPU, NVIDIA GPU you run it on. So, and we kind of talking about this earlier. If you have a scikit learn pandas notebook and it's not GPU accelerated, right? You add that magic command, those two magic commands at the top, run it in a Colab Enterprise on an L4 or an H100, whatever, depending on how much data you have. And it doesn't matter. That same code is going to run on any of those GPUs. And if you want to run it on the CPU, if you have very, very small data, comment out those magic commands, and that same notebook is going to work either way. The library stays the same.
And on dataset size too, I think that was part of the question. You can absolutely have a data set that's too large for like an L4 GPU. You'll run out of memory on the GPU. You could do a couple of things. You could you could do what Will had mentioned and use more of a distributed architecture where you have multi-nodes. You could change the GPU you're using. There are a lot of different options you could think about when you're running up against dataset sizes as well.
I noticed both of you in both your demos, one of the first thing you did was take a look at the RAM for both the CPU and the GPU. And I felt like you were continually checking back into that as your jobs ran. It feels like a lot of this is, do you have any advice around memory management for folks who are starting to do this?
Yeah, actually, like interestingly, when we think about data, there are different data types. And for example, when I was showing some of this climate data, when I had initially started putting this together, things were strings or they were int 64s, and int 64 takes up a certain number of bits. But if you change it to an int 32, which you might be able to do without any loss, depending on your data, that all of a sudden reduces the memory footprint of that specific column by like half. So there are definitely ways to manage your memory that aren't just like staring at the little green that turns red line and watching that tick up. There are memory management techniques that you can think of there. Another might be, hey, I create a data frame and then I create a copy of the data frame and then I do something with that and I merge it to another data frame. You can prune those old data frames that you don't need and you can get rid of them and drop them from memory. So there are a lot of things you can do to on the memory management side. It's not all automatic, but it is relatively straightforward to do if you need.
Yeah, and one thing I like to do, if I find my memory blowing up, these libraries work directly with Google Colab and other Google services, so I can read from storage directly. All right, so if I find, all right, my data set is starting to bump up against the limit, I can just save it up to Google Cloud Storage as a Parquet, get a bigger runtime, get a bigger GPU, and then read that data directly from Google Cloud or BigQuery, wherever it's stored, right into my data frame once I have a bigger NVIDIA GPU.
That feels like a good tip. Another question from the chat. I feel like we touched on this earlier, but I think it'd be good just to revisit here as we start wrapping up. So what is a good heuristic to help us know when it's appropriate to look at GPU accelerators? Is there a reliable insight or a check or a report that is a signal to you that you might want to start considering GPU acceleration?
It's emotional for me, Greg. It's emotional. Yeah. I'm
impatience.
I'm impatient. Yeah. If I'm in the middle of vibe coding and it's going slow, I'm gonna get a GPU and put that magic command. Jeff, you probably have a better answer than that, but I don't like waiting. I'm gonna put that magic command at the top and then go back to coding. Yeah.
Yeah, I think it depends on how long running are your operations, and could they be something that could be, is it something that could be accelerated by GPUs? If your code's taking, your data frame operations are taking, I don't know, substantially longer than you would expect, you might want to just check out, does this run on a GPU? Let's just check it out. You don't need to spend a lot of time on it. Again, you just load that one magic command, try it out, see how it runs. And then shut down the GPU when you're done. So I would just check that out depending on how long things are taking. Now, a lot of people don't run things on 3, 4, 500 million or billions of records, and that's totally fine. If things are running for you and they're fast with pandas on a CPU, that's great. So keep that in mind. You don't need a GPU for everything. And in fact, most people aren't running workloads on huge amounts of data. So I wouldn't use a GPU just for the sake of it. But the option is there.
That's cool. As we wrap up, Jeff, you have any other comments, thoughts that you'd like to give to the folks who are trying this out?
I would just encourage people to check out the learning paths and see whether this is something that would work for your workloads. When I think about how did I start using GPUs, again, until probably early last year, I would think of GPUs as these things that we would use to train large language models, or again, to make video games run better on my PC. But when I started applying them to my data work in Colab Enterprise and then in other technologies like Cloud Run, I was just kind of blown away by what was possible with GPUs. So I would just encourage people to tinker, try it out, see how it works for you. Maybe it doesn't work for you, maybe it does. But just getting your hands dirty is my best advice.
Yeah.
Will, what about you?
Yeah, as I'm thinking, there's a couple of things I guess I would point out. And the first is these are open source. These are on GitHub. If you Google NVIDIA CUDA GitHub, you're going to see the code there. And this is a very welcoming open source community. So, or if there's a function you want parallelized, or if you want to submit a PR, I did this recently, and one of the developers named Simon, embraced me, didn't make fun of my code, right? So it's a very welcoming open source community. If you want to submit a bug or a PR or a feature request, do that. The other thing is, we talked a lot about notebooks, but Jeff, you mentioned, Cloud Run, right? So that's not a notebook environment. That magic command, if you're running just a Python script or, a cloud function or something, you actually just, it's 2 lines of code at the very top. It's an import and then a pandas qdf.install function. Does the same thing as that magic command. There's also in the command line, right? Where you do Python script, you're just going to do a -m qdf.pandas or a -m coolmlxl, right? And so cloud, any of those functions or Cloud Run, whatever it is, you can do the same thing, not in a notebook. I think I guess we should point that out as well.
That's a great distinction. Well, I want to thank you guys. If nothing else, for me, I feel like you've made GPUs so much more tangible today, and giving folks, even if their primary interest is on, training LLMs or inference, like I think there's so much talk about GPUs that you've offered here a way that folks can really tinker and get a really strong feel for the difference between GPUs and CPUs. But then also, of course, it's just this incredible application in data science and working with these incredibly large data sets very, very quickly. And so this has been awesome for me. Thank you so much for this conversation. I can tell from the chat, a lot of folks also really enjoyed it. If folks are watching this, and you want to learn more about this stuff, I would ask, please come join us in a couple weeks at Google Cloud Live. It's in, at Google Cloud Next. This is Google Cloud Live. This is our huge show in Las Vegas. It's April 22nd, 23rd, 24th in Las Vegas. Jeff, you're going to be there, right?
Yeah, Will and I will actually be there talking about this similar topic. So come talk to us. We'd love to share more and talk with any devs there.
All right, so you guys are you're going to be giving a talk, and if folks want to ask you questions in person, they can come find you, and that'd be awesome. So we'd love to meet. If any of you are watching, please, if you do join us in Vegas, please come say hi. That's Google Cloud Next in Las Vegas in just a couple weeks, April 22nd, 23rd, 24th. Would absolutely love to see you there. There's just a few tickets left. We're like, don't wait too long to buy your ticket, because I don't know if there's going to be many more available here. But that wraps up today's show. Thank you all so much. Jeff, Will, thank you so much for teaching us all this great stuff. And for everyone who's watching, thank you for joining us, and we'll see you next week.
Cheers.
Thanks all.